Okay. I will not remove one clause every class, don't worry. I will stop here. Okay. So let's do a 1-hour class on Bernoulli percolation, and let's see how far we can go. Okay? That's usually it's one term, so a little bit compressed, but let's see if I can at least convince you of a few facts. So, second, Bernoulli percolation. So Bernoulli percolation, the measure, I mean, you can in fact define it directly in infinite volumes. There is no problem in doing so. What you do is just every edge is open with probability p independently of others. Okay, so for every p between 0 and 1, you can define this measure directly in infinite volume. So let's see first what are the basic facts about this. What do I know? What are the basic properties of this percolation? And that's where I will not define, I mean, not prove things. First, because the proofs are very simple, and second, because I don't have no time. So these basic facts, basic properties, they are related to the notion of open, increasing events, sorry. So an increasing event is what? So you see that if you have two configurations on ZD, you have a natural ordering on pairs of configuration that you can say that omega is smaller than omega prime if omega e is smaller than omega prime e for every edge. Okay, it's a partial ordering, but it's an ordering. And in particular, this defines a notion of increasing function. Which is going from 0, 1 to the edges into R. Okay? But if you have a notion of increasing function, you also have a notion of increasing event by saying an increasing event is an event for which the indicator of A is increasing. Another way of seeing what an increasing event means, you can simply say that if that's an alternative, just, I mean, a rephrasing of that is if omega is in A and omega is smaller than omega prime, then omega prime is in A. So increasing events are stable by opening edges. Now, why do I introduce this type of things? Well, because there are a few properties of percolation with respect to these things. The first one is the monotony. So monotonicity is doing the following. If A is increasing, this will just mean increasing. If A is increasing, and if P is smaller or equal to P prime, then the probability of A at parameter P, it's smaller than the probability of A at parameter P prime. This is very natural. You expect that the larger the P, the more open edges you get. And in fact, if you want to prove this, it's not very difficult. What you do is you notice that you can define all the percolation configuration on the same probability space by doing the following. Take omega to be 0, 1, or let's say omega bar to be 0, 1 to the edges, and put a uniform random variable, 0, 1, on every edge. Okay? Every edge has its own uniform random variable. Now you can define omega p of E to be simply 1 if UE is smaller or equal to P, and 0 otherwise. You see that every edge in this case is open with probability P and closed with probability 1 minus P independently of the other edges. All the uniform are independent there. But now you have automatically that the probability at P of the event A is what? Is the probability under this big measure. This is going to be the measure with uniform variables. The probability of omega P in A. This is the same measure. But now omega P is smaller than omega P prime by construction. So since A is increasing, this tells me that this is smaller than the probability of omega P prime in A. And now this is just the probability at P prime of the event A. So this is a very simple monotonic coupling between the different percolation configuration. And so you deduce this quantity. And this is going to be important for us. There is another property which is important, which is the FKG inequality. So the FKG inequality says the following. If you take A and B increasing, then the probability of A intersected with B is larger or equal to the product of the probabilities. So if you divide by the probability of B, you see that the probability of A knowing B is larger than the probability of A. So it's saying that they are positively correlated, increasing events, which is very natural because an increasing event is an event that likes to have open edges. So if you condition on the event B, you are pushing the configuration to be bigger, so it's simplifying the life of A, simpler for A to occur. Okay? I'm not going to prove that just because it's very simple to prove. You do it by induction on the number of edges on which A and B depend. So I never said that A and B were depending on finitely many edges. For infinitely many edges, you just use an approximation of increasing events by increasing events depending on finitely many edges. So here it's a basic exercise as well. So by induction. I'm not going to spend time here. But the intuition is really what I just mentioned. Then there is another formula that we are going to need for increasing events is Rousseau's formula. So Rousseau's formula is saying the following. If A is increasing, then the derivative of the event A is simple to compute. So let's say A depends, increasing depending on edges in a set E, which is finite. So I only look at event depending on finitely many edges. So this differential is going to be equal to the sum for the edges in E of the following quantities. The probability that E is pivotal for the event A. What does it mean to be pivotal? That means that a configuration omega belongs to this event if when you turn the edge E to be open, so you take your configuration omega, you turn the edge E to be open, then you are in A. But if you turn it to be closed, then you are not in A. So that means that in this configuration, somehow, the edge E is deciding whether you are in A or not. So a typical example, if you want, for instance, that a point is connected to the boundary of a box, an edge is going to be closed, an edge is going to be pivotal. So this edge is going to be pivotal if what? Well, when it's open, I need to have a path from 0 to the boundary. Okay? So I need to have something like that. But when it's closed, so imagine this edge is closed, it's like blocked. I need somehow to have a set of closed edges which is surrounding the origin that is preventing 0 to be connected to the boundary. Okay, so that means there are many other edges like that. That are closed. Okay? So this is a typical example of a pivotal event. So how do you prove that? I mean, there are two ways. First, you can use a grand coupling and do it. It's a very cute proof. It's very simple. The reason why it's going to be the edges that are pivotal is that when you look at p plus epsilon and you look at the difference with the percolation parameter p, you have very few edges that are switched from closed to open. And when epsilon tends to 0, typically you have 1. And this edge needs to matter, so it needs to be pivotal for A. So you can do the proof like that. Otherwise, you can just be more pedestrian and just say, well, the probability of A is what? Well, it's just the sum of a configuration of p to the number to the sum of the omega e, 1 minus p to the sum of the 1 minus omega e. So this is a number of open edges. This is a number of closed edges. Indicator of the event of omega is in A. OK? This is the formula. Well, differentiate that and just put things together, and you get exactly what you want. There is no mystery there. You can just differentiate like that. It's completely fine. You will fall exactly on this quantity. For those who never saw the Rousseau's formula and didn't understand what I explained, just at the end of the class, you can come and I will just do the proof. I mean, it's a very short proof, but I don't want to lose time here. Well, that's the only thing I'm going to use. I'm not going to use for people who know the BK inequality, which is much harder to prove. This I'm not going to use. Well, I'm going to use something that looks like the BK inequality, of course. This was, these were the basic properties. Now, let's talk about the phase transition. And the first theorem I'm going to state, and it's a trivial theorem, is that for every d larger or equal to 1, there exists a PC, which depends on the dimension, and it's between 0 and 1, such that the probability that 0 is connected to infinity, there is a path from 0 to infinity, where this quantity is 0 if p is smaller than pc, and strictly positive if p is larger than pc. Okay? There is what we call a critical point. There is a point which is distinguishing between there is no infinite cluster, there is no infinite path, and there is an infinite path going to 0 with positive probability. And you see that this theorem is basically trivial to prove. As stated, there is basically nothing in it. Why? Because you can just define PC to be the infimum of the P, such that the probability that 0 is connected to infinity is strictly positive. Just define it like that. Since I have, since this probability, this event is increasing, this quantity is larger and larger by the monotony property, and I'm done. Okay? So far, so good. So this was a trivial statement. But now I want to say a little bit more about that. So first, notice that the percolation measure is invariant under translations. Okay? You take a lattice translation, the percolation measure is invariant. In fact, it's fairly easy to prove that it's ergodic. So here, the measure is ergodic, meaning that if A is invariant under translations, then the probability of A is either 0 or 1. So you can try to prove it as an exercise. It's not very difficult. What you do is you take your event A, you write that A is A intersected with A. You approximate A by an event depending on finitely many edges. So you say that it's close to AN intersected with AN. And then you translate one of the AN very far. So now the two events are depending on completely different set of edges. They are independent. So it's basically probability of AN squared, which is basically probability of A squared. Once again, this, if you never saw this proof and you want to see it, come at the end, ask me, and I will just take 10 minutes and explain it line by line. But what is the, I mean, why is it good to have this? Because now it tells me that, in fact, in this context, okay, the probability that 0 is connected to infinity is strictly positive and cannot be 1 because, you know, all the edges around 0 could be just closed. But the probability that there exists somewhere an infinite cluster, this has to be 1 if P is larger than PC. In fact, as soon as this probability is strictly positive, then the probability that there is an infinite cluster is strictly positive, but then it has to be 1 because that's an event which is invariant under translations. Okay? So there is really a clear phase transition in the sense there is a clear change of behavior in the macroscopic properties of the model between a phase where there is no infinite cluster almost surely and a phase where there is an infinite cluster almost surely. Okay? That's the first interesting thing. So this is already a little bit less trivial than this theorem. Now an even less trivial thing, and in fact highly non-trivial at the time, was to prove that when the infinite cluster exists, it's unique. And this is a beautiful argument. That's basically when I saw this argument that I fell in love with percolation. Then I saw, then I will not manage to translate it well here, but the following theorem, which is due to, in fact, it's not due to Burton and Keene. It was first proved by Kesten, Eisenman, and Newman, but in a proof that was very difficult. I mean, not very difficult, but harder, and definitely less general. This one will apply. I mean, it's important I present it because I will use it for random current later in the class. So a theorem that is saying probability that there exists more than 2 infinite clusters is always 0. So this means that either there is 0 infinite cluster almost surely, or there is 1 infinite cluster almost surely, but never more than 0 or 1. And here, be careful, it's on ZD. This is extremely important because it's just not true in general. So let me present quickly this argument because it's a beautiful piece of mathematics. And it's extremely general. You can use it in many contexts. It has been used in many contexts. And it's enlightening. OK. So let me define first 3 events. Okay? I'm going to define E smaller or equal to 1, E smaller than infinity, and E infinity. There are going to be 3 sets. This is a set that they are less or equal to 1 infinite cluster, so 0 or 1 infinite cluster. This is finitely many. And this is infinitely many. So the first step, and this is going to be the simple step, is going to be to prove that, so this set is included in this one, okay? If there are less than 1, I have finitely many. So the first step is going to be to prove that, in fact, the probability of this minus this is 0. If I have finitely many, in fact, I have only 0 or 1. And the second step will be to rule out the fact that maybe I have infinitely many of them. So in order to prove that you have, I mean, if you have finitely many, then you have only 0 or 1 infinite cluster, what you can do is the following. Since you have finitely many, there exists a rank, a size of box, for which the box is intersecting all of the clusters, the infinite clusters. Okay? If you have infinitely many of them, it's not true, but if you have finitely many, it's true. So just choose a capital N such that the probability that all clusters touch lambda n, let's just assume this is larger than 1/2 of the probability of E minus infinity. Okay? You can always find the n such that you have that. Okay? Probability, so you can find n a size large enough so that all the clusters touch the box with probability at least 1/2 of the probability that you have finitely many clusters. But now, you see, all clusters touch the box. This doesn't depend at all on the state of edges in the box, by definition. Okay? So you can open all the edges in the box. It will cost you p to the number of edges. And now you have what? You have all your clusters touching the box, and all the edges inside are open. So you have what? You have a unique infinite cluster, or zero infinite cluster if you didn't have any infinite cluster to start with. But this thing tells you that the probability that there exists a unique, I mean, there is less or, well, probability of E smaller or equal to 1 is definitely larger or equal to p to the number of edges in lambda n times this probability. So this is larger or equal to p to the number of edges over 2 times the probability of E smaller than infinity. But now, this is an event which is invariant under translation. This is an event that is invariant under translation. So the only possibility is that either they are both equal to 0 or they are both equal to 1. But then, in both cases, the probability of this minus this is 0. So ergodicity implies that this thing equals this thing. And by the way, belongs to 0, 1. This is one of the byproducts. Okay? So ruling out the fact that you have finitely many clusters is very simple. Now let's try to rule out the fact that you may have infinitely many of them, and that's the interesting part. So assume that this thing is strictly positive. It's outside. Okay. So in this context, what you can do, you can choose n. So you cannot choose n such that all the clusters touch the boundary of your touch your box, but you can definitely choose n in such a way that at least 3 of these clusters touch the boundary. This is doable. So choose n such that the probability that 3 clusters touch the boundary, touch lambda n, is strictly positive. This, there is no problem. You have infinitely many of them. So if you look at the first n for which you find 3 of them, you are done. But now you see, so you have 3 infinite clusters. I mean, at least 3. So let's just draw 4 to give us courage. Once again, it doesn't depend on what is inside, a priori. So now inside, what I can do, I can look at 0, look at 3 edges starting from 0, and connect them like that, and close everything else. You close everything else. If you do that, you end up with a configuration such that 0, if you disconnect 0, you have 3 infinite clusters coming to a neighbor of 0. Okay, this cluster never touch, because here I'm taking clusters that really never touch outside. Okay? So if I disconnect here, I have 3 disjoint clusters, but if I look at the fact that I can pass through 0, then I have only these 3 guys are in the same infinite cluster, in fact. Okay? So this point is called a trifurcation. And we are going to call this event CT0. Okay? Oh, well, no. Let's not even call it CT0. let's not give names. So this is called a trifurcation. And the consequence of the fact that there is infinitely many clusters is the fact that the probability of a trifurcation is positive. There is a positive probability of getting a trifurcation. The probability that, in fact, X is a trifurcation is positive. I mean, it's larger or equal to a certain constant A, which is positive. OK? I mean, in fact, equal. So in particular, the expected number of trifurcation in lambda n, in a box of size n, well, it's simply A times the size of the box. OK? OK, that's so far so good. Nothing very surprising there. But now, these trifurcations, they have a very specific behavior. So let's draw this big box lambda n. And let's say this is my first trifurcation. So this is going to infinity, this is going to infinity, this is going to infinity. Let's assume I have a second trifurcation. What are the possibilities? Well, first, the trifurcation could be on one of these things. But in this case means there must be a path here going necessarily to a new point on the boundary. Why? Because I have three Dijon clusters. One is this one is this one, and I need to have a third one. So I have a third one, and it has to end up, it cannot end up here, here, or here, because otherwise these three clusters will not be disjoint when I disconnect here. OK? So if I add a trifurcation, necessarily there must be a point on the boundary. So this was one possibility. If you carry on like that, you will get another one. It could also be that the trifurcation is not on what you already discovered. But in this context, you are adding even 3 points on the boundary. So as soon as you have one additional trifurcation, you have one additional point on the boundary. So the number of trifurcations, by definition, has to be bounded by the size of the boundary. So number of trifurcations so the expected, in fact, it's even deterministic, but as a corollary, the expected number of trifurcations has to be bounded by the size of the boundary. When n tends to infinity, you discover that A is smaller than the size of the boundary divided by the size of the cluster. It tends to 0 when n tends to infinity, so A has to be equal to 0. So in fact, my assumption that there were infinitely many clusters is contradictory, absurd. Okay? It's a beautiful argument. It's completely straightforward. It works in great generality, so in the generality of many more models. In fact, also you can see here that we only use some isoperimetric inequality. So in fact, it would work on any amenable Cayley graph, for instance, or things like that. So it's very general. It's sharp. It's a beautiful argument. But really, I want to highlight the fact that the original proof was not easy at all. I mean, this is a perfect example in percolation of a beautiful proof that came after much more difficult ones. So, I mean, they are very simple proofs, but they took time to be discovered. So, I mean, when I saw this proof, I was really, so that's just too beautiful. I mean, I need to do percolation. And then you realize that you don't find proof like that, and then you're a little bit upset. But especially, I mean, the epiphany is usually very short, because what is the next theorem that you prove after that? Well, the next thing is you want to understand. So now, you see, we have that in the supercritical phase, there exists a unique infinite cluster almost surely. So now, say the supercritical phase, we have a basic understanding of what is going on. So what is the next question is to have a basic understanding of what is going on in the subcritical phase. And the theorem that you want to do, to get, is the following, is that if P is big, if P is smaller than PC, then there exists a constant, which depends on P and D, such that the probability that 0 is connected to the boundary of the box of size n is decaying exponentially fast. You want to understand, you know it's decay, it decays. You want to understand at which speed. And the truth is it decays exponentially fast as soon as you are in subcritical. So you see you are like, so you are in Orsay, it's beautiful, you have the trees outside, and Wendelin is explaining this proof, and you are like, okay, I want to do probability and percolation, and then he presents this proof. And this one is much, much tougher somehow. So what I propose is that I'm going to give you an argument that is not even online yet. We wrote the paper, but we are a little bit slow on the possible application. So it's a very recent proof of this statement, which I believe is much, much shorter than, I'm sure it's much shorter. I don't know if it's better, but I'm not even sure it's true. No, I think now we are pretty sure it's true. So a much shorter proof of this fact. Just historically, this is due to Eisenman and Barsky, and in fact, 1 year later to Menshikov. So 86 and 87. And they are like 30 pages long papers, extremely interesting. I personally, I'm very fond of the Eisenman-Barsky paper because they are beautiful connection to the Ising model and to quantum field theory. But somehow, I still think that there was a better way to do, so shorter way to do. So how do I prove that? So I should really say it's a joint. This is a really joint work with Vincent Tassion. Let's try not to destroy completely the thing. Okay, let's take a set S included in ZD. And let's define delta S is going to be the set of edges, x, y. It's edges of ZD, okay? Such that x is in S and y is not in S. So, visually you have your set S, and that's these edges, okay? And let's define the following quantity. Will look a little bit strange to you at first, I guess. The quantity is, let's define phi p of S. It is the sum, it's p times the sum for x, y in delta S of the probability that 0 is connected to x in S. Okay? So I look at, so by the way, x here, I will really always keep the notation that x is in S and y is not in S. Right? So I'm just looking, what is it? It's p times the expected number of points that I can reach from 0 in S. Okay? So for instance, just an example, phi p of just 0 is what? I have 2D neighbors. So no, but no example. This is not a good example. Okay. No, it is a good example. No, it is a very good example. So it's p times the sum. So the only x that you can reach from 0 in 0 is just 0, okay? And you reach it with probability 1. So this is 1, but I'm summing over all the guys. So I get 2D. I have 2D neighbors, okay? And you can define, you can compute this for more general values. Now let me define PC tilde to be the following quantity. PC tilde is the infimum of the P such that phi P of S is larger or equal to 1 for every S containing 0. S is finite as well, okay? It's finite. So what do I look at the first edge parameter for which phi p of s is always larger or equal to 1 for any s. Okay? Any bet what this PC tilde is? Well, if I call it PC tilde, there is a good reason. This is in fact PC. That's what we are going to prove. We're going to prove that this is a characterization of the critical point of percolation. It's a value for which, when I do p times the expected number of points I can reach from 0 in a set S, whatever the S, I get something larger or equal to 1. Okay, so let's try to see why it is indeed. So, I mean, this proof is not that simple, okay? I mean, don't worry if, but it's self-contained. Let's try to see why, for instance, assume P is strictly smaller than PC tilde. And what I'm going to do, I'm going to prove there is exponential decay in this context. Okay? So if I take P smaller than PC tilde, what am I doing? I'm just taking a P for which I know that there exists a set S for which this thing is smaller than 1. Okay? Let's choose this set. So choose S such that phi p of S is smaller than 1. And let's assume that S is included in the box of size lambda L minus 1. Okay? There is a, just take the radius, L. Now I want to argue, I want to look at the probability, maybe let's do like that. I want to look at the probability that 0 is connected to the box of the size, say, n times L. Okay? So if I have a path, let's do a drawing here. If I have a path, so I have my set S, and I have a path from 0, which is in S, to the boundary of the box of size n times L. If I have this path, notice that there must be a point. So first, I mean, for people who know the BK inequality, this is fairly simple to prove. But I want to just avoid using the BK inequality. There is a point x and a point y, such that 0 needs to be connected to x in S. So here, let's say, here you have x. Here you have y. So you need to have 0 connected to x in S. You need to have x, y open. And you need to have y connected to the boundary, not using what is before. Why do you need to have something like that? You have two ways of seeing it. You can say that if there is an open path to the boundary, there is a safe avoiding path to the boundary. Okay? And so if you take the first exit point, it will exactly have these properties. So for people who know the BK inequality, you have disjoint occurrence of 3 events. You can just use the BK inequality. I don't want to use it, so I'm going to just change a little bit, and I'm going to say, look at the cluster, the set C. It's a set of x in S, such that 0 is connected to x in S. It's not, let's call them Z. So it's the cluster of points that you can reach from 0 in S. Okay? So here, what I can do is I can say, if I have a path from 0 to the boundary, then there exists an x an xy in delta S, such that 0 is connected to x in S. Okay? xy is open. And what? And y is connected to the boundary of the box, but in C complement. You can just check. You have a certain cluster of points. You have these are all the points that you can reach from inside. There must be somewhere a point where you go from y to the boundary, this edge is open, and this guy is connected inside. and where this guy is not using the yellow part. Just try to convince yourself on the picture. It's completely straightforward. But now what you can do is you can say, OK, let's condition on C. Let's just say, OK, this is the sum. So first, it's smaller or equal. Let's smaller or equal to the sum of the xy in delta S of the probability of this event. OK? This is just a union bound. And now, condition on C. So this is the sum of xy in delta S, the sum of a possible realization C of the probability. So I'm going to have xy open. I'm going to have 0 connected to x in S. I'm going to have C equal C. Okay? So this is one possible realization of this cluster. So I'm fixing the cluster. And I'm going to have y connected in C complement to the boundary of the box. Right? I just use a union. I mean, I just use that this thing is a disjoint union. Just that. Okay? But now look. This, and this depend on completely different set of edges. So they are independent. So I can say that this is this times this times this. Yes? But now this, I want that y is connected to the boundary of the box of size NL in the complement of C. But y, by definition, because S is included in lambda L minus 1, y is in lambda L. So y has to go at least to distance n minus 1 times L. And this is just making it even harder. So this quantity is smaller or equal to the probability that 0 is connected to the boundary of the box n minus 1 L. Okay? Because you can forget that, and you can use that this is in lambda L. This is equal to P. And when I sum over C this quantity, I get, so the sum over C of this quantity is just equal to the probability that 0 is connected to X in S. So what do I recognize? I recognize, so I have this, so it's smaller or equal to the probability of this. Sorry, it's maybe not readable like that. And here I get P times the sum over the edges of this. This was exactly the definition of phi P of S. So I decrease the distance by L. I multiply by phi P of S, which is smaller than 1. I iterate that. I get a bound, which is smaller than phi P of S to the n. I have exponential decay. Okay? If you think this is a little bit messy, just do with BK, or just redo it yourself. There is no here. I mean, this is perfectly rigorous what I wrote there. There is no. I'm not cheating you at any point. Okay. Very well. So I'm going to be done if I can prove that for now P bigger than PC tilde, I would like to prove that I have an infinite cluster in this context. And then I'm done. OK. Let's try to do that. If you have questions, please do ask. There is So let's fix n. And let's look at the derivative of the probability that 0 is connected to the boundary of the box of size n. Okay? So by definition, this we said, it's the sum over xy of the probability that xy is pivotal for the event 0 connected to the boundary. Right? This is Rousseau's formula. Now notice that being pivotal doesn't depend on the state of the edge xy. Right? I mean, since anyway, when you say a configuration is pivotal, you say if I change the state of the edge to open, I'm in A. If I change it to close, I'm not in A. So it doesn't depend on the edge of the state of the edge xy. So here I can add, if I wish, I can say this is 1 over 1 minus p times the sum over xy of the probability of the same event, but I can also add xy is closed. Why not? Okay? So I just, this is the probability of this is 1 minus p. It's independent of that. So if I divide by 1 over 1 minus p, I get the same thing. And now here is a trick. Define S to be the set of x in lambda n such that x is not connected to the boundary. Okay, it's a random subset of the box. It's the guys that are not connected to the boundary. Okay? And let's do exactly like there. Let's write let's distinguish xy closed and let's say S equal capital S. Okay? Let's do like that. Let's just cut this probability into the different subcases where I'm fixing the set S. Notice that because xy is, because I'm looking at a pivotal set and that I'm saying xy is closed, if I have a closed pivotal, by definition, my event is not occurring. Okay, the edge xy is pivotal if when it's closed, the event is not occurring. So since I'm fixing it to be closed, the event is not occurring. What does it tell me? It tells me that here I can restrict myself to sets that are containing the origin. 0 is not connected to the boundary, so it's always in S. Right? I'm almost done, don't worry. So I have my set S. These are the guys that are not connected to the boundary. So that means that every guy here is connected to the boundary, right? What are the pivotal edges in this set? In this, if I look at a configuration where I know that S is a set of points that are not connected to the boundary, what are the pivotal edges? So if this guy is a set that is not connected to the boundary, in fact, this is somehow the, for those who want to see it that way, it's kind of the exterior most blocking surface somehow, right? Where are the pivotals? I mean, the pivotal cannot be there, because anyway, if you change the state of edges outside, that's not going to change because this surface here will still be blocking. So even if you turn it to open, the event will not occur. It cannot be in either because, I mean, for the same reason, this blocking surface will remain blocking. So the only possibility is that the pivotal edge is on this surface. That's the only possibility. Right? Good. But at the same time, I want it when it's open that there is a connection. So that means that the site X here, it has to be connected to 0 by an open path in S. There is no choice. Otherwise, it's not working. So the expected number if I sum over S equal S, the expected number, the sum of the edges of the probability of being pivotal, so the expected number of pivotals, it's what is just the sum over x in over xy in delta S of the probability that 0 is connected to x in S. This is exactly the expected number of pivotals. Right? And we still have probability that S is equal to S. So, I mean, okay, maybe, no, sorry, I went a little bit fast. So it's the sum of the edges of the probability of being, this edge is pivotal. So this probability, you need to have S equal S. And then you want 0 connected to X, but this is occurring only in S. So it's independent of this event. So I should write it like that. Sorry. Just for you to. So this is exactly the probability that the set xy is, that the edge xy is pivotal. But because this is depending on edges outside S, and this is depending on edges in S, this thing is just the product of the probabilities. Right? Sorry. I mean, I jumped this step and it was maybe too fast. Okay? So now it's complete. So I use that, deciding that this is a set of non-connected sites requires only to know the boundary and the outside, not what is in S. So independence helped me to do that. So here I notice that this quantity is just 1 over p times phi p of S. So it's bigger or equal to 1 over p. So this is larger or equal to 1 over p. So all of this is larger or equal to 1 over p times 1 minus p times the sum over S equal S of the probability that S is equal to S. And remember that S, I mean, sum over S. Remember that 0 is in S. Huh? But this is what is probability. So it's the sum over every possible subset S of the probability that S is equal to S, but subset that contains 0. So this is just the probability that 0 is not connected to the boundary. So all of this is equal to 1 over p, 1 minus p times the 1 minus the probability that 0 is connected to the boundary. So what did I just prove? I proved that for any, and I'm done. Basically, I will release you. So that tells me that the derivative of 0 connected to the boundary is larger or equal to 1 over p, 1 minus p, times 1 minus the probability that 0 is connected to the boundary. And so now I think that this is a differential inequality that everybody can handle. It tells you that this thing, so this is true for every n and for every p larger than pc tilde. So it tells you that this probability is larger or equal to p minus pc tilde over p1 minus pc tilde. You just integrate the differential inequalities, that's what you get. Well, so because this is uniform in n, it also tells you that the probability that 0 is connected to infinity is larger or equal to that. So note for the specialist that it also gives you the mean fin lower bound automatically. And really, I mean, I didn't hide anything under the carpet. This is a completely self-contained proof. I mean, when you see it like that in 20 minutes, it's a little bit fast, of course, but if you go in the lecture notes and you read it again, I mean, it's really, there is nothing hidden there. It's a one-page proof. I mean, 1 page and a half. Okay, I guess we are going to stop there, and next week we will carry on and deduce, for instance, that PC equal 1/2 on Z2, speak about a very short proof of Rousseau-Seymour wedge due to Bolobash and Riordan, And then we will dive into dependent percolation models and see what we can do in this context, what we cannot do anymore, and so on. Thank you very much.